Hello, everyone, and welcome to Iron Beetle, the show where we learn how to create a modern distributed database which is highly reliable, which doesn't allocate at runtime, which is implemented in Zig, which only tracks financial transactions and, in a sense, can be called a NoSQL database. And today is very exciting episode. It is sort of capstone episode of the arc which spanned the last, I don't know, maybe 10 episodes or something like that. So, kind of like where we are at a target middle. We are discussing storage engine, how we actually represent the result of transfers on disk. And we covered almost everything about it. In particular, we now understand the static layout of data on disk. So we understand what is the superblock, what is the grid, what are levels of LSM3, how levels of LSM3 are encoded into manifest log, which is linked to from the superblock, etc., etc. We understand like roughly the checkpointing process. So kind of like when the time comes to the checkpoint, we replace the superblock, and that kind of like in one go replaces the static picture. Recently, we've been looking at the in-memory part of this whole storage engine. Because again, one of the big ideas of Trigeminal is batching. And when applied storage engine, that means that you are not applying changes to disk immediately as you process transactions, but rather you first batch your changes in memory and then apply the whole batch of changes to disk. And it is safe in a sense that even if you crash, you are not losing anything because the original prepares, the original requests are still in your write-ahead log. So after the crash, you could start from a checkpoint, you could replay all the transactions and arrive at the same, at the exact same memory state. So basically, we covered more or less everything except the key thing, how the state on disk actually evolves. We know that when we do a checkpoint, we replace the whole state by an updated state, but we haven't actually talked about rules of updates. And this is a complicated topic. We'll start on it today. Hopefully, my brain won't melt, although given the temperature here in Portugal, it is highly likely that my brain would actually melt. So let's start. And before we dive into the code, let's draw some pictures. Okay, so LSM tree consists of levels. So let's, for simplicity, draw something like 5 levels. What are the levels? Oh dear, oh dear, it looks like I am frozen. No, I'm not frozen. Okay. But I definitely forgot to actually share my screen, and that was a mistake. Okay, so now it is much better. Okay, so levels. What are levels? Levels store tables. Let's schematically represent tables as just boxes, but okay, let's say that level is this thing, so we'll make the box slightly smaller. Okay, so we have levels. Inside each level, we have tables, and actually kind of like, the thing here is that levels below generally tend to have more tables. Okay, so this is 1, 2, 3, 4, 5 level of LSM tree. So each table here is a set of a sorted set of keys and values. And the rules here is when you want to retrieve data from the tree, you traverse it from the top down, and the first level where you find your key is correct. So let's say you are looking for key bar. So we interested in what is equal to bar. And let's say like our first level says foo equals 1. And in the second level, we have something like buzz equals 2. And in the third level, we have bar equal 3. And in the fourth level, we have bar equal 6. So in this picture, we kind of like going to traverse this path through the tree and stop at this bar. Kind of like this bar shadows a bar below it. Okay. And this means that our LSM tree has a certain amount of physical redundancy. So although kind of like, well, let's say in this table, like we have like bar equal 3 and like full, well, q equal 1. And here, I don't know, for example, we will say, well, just say that, okay, it's just bar equals 6. So we have like, certain amount of physical redundancy here, where like this record of bar equals 6 doesn't really matter. It doesn't really contribute to useful payload because the records on top of it fully dominate it. And this is the idea. Oh, sorry, behind compaction process. So we take two tables. Well, not necessarily two tables. We take two levels. We take one table from the first level and all the tables from the next level which intersected in terms of key range, and then we merge the table. So we essentially run a merge step of a merge sort over all the input tables, with the rule that if we've already seen the key, then we kind of like not output on it. So because, well, it kind of like got evicted. So in this sense, if we like merge these two tables, what we actually get is just this bar equal 3. And then we can write the resulting table into the level which was lower. So this is kind of like the rough idea behind compaction. Now, uh, how do we actually do this? And this is tricky. Like, normally in databases, compaction runs as some kind of a background process. So uh, there is like a thread which periodically reads levels of your LSM tree, finds levels which are full, uh, takes some tables from one level, some tables from the other level, merges them together, writes them in the output level, and that's it. And kind of like, informs the main process that, hey, I kind of like created this new table. So by the time that the next checkpoint and process, checkpoint and point happens, we kind of like substitute those new tables. The problem with compaction in the background is that it gives you non-deterministic results, kind of like dependent on when the compaction thread gets scheduled relative to the thread which actually processes transactions, you might end up with different physical data on disk. Logically, the data will be the same, but physically, representation will be different. Normally, that's not a problem. But for Target this is a problem. Because, as a reminder, Target assumes that the disk can fail. And because of this, Target implements pretty smart protocols for repairing corrupted data on disk. And if you go to the grid and take a look at the core function for reading data from disk, read block, you see that kind of like the result of this block doesn't of this read block doesn't have affordance to show an error. Like, you ask the grid, hey grid, please give me a block, and the grid always gives you a block. And the reason why this works is because the grid transparently repairs corrupted blocks from the peers. So if it so happens that you read the block from a local disk and the checksum mismatches, the grid doesn't even bother to tell the caller that there was an IO error, that the checksum was wrong. Instead, the grid transparently asks a different replica to give it the same block, and the replica gives it, and then kind of like the grid just resumes as if this was a block from grid's local disk. To make this work, though, you actually need to make sure that the data on different replicas is not only logically equivalent, but it is actually physically equivalent. So if, for example, we are using this background compaction, and background compaction runs at different speeds on different replicas, then although the replicas will store the same data logically, physically the blocks will be different, the checksums will be different. So this simple approach for repair, which repairs on a physical level, simply would not work. So we kind of like have to make compaction deterministic somehow. And the idea behind deterministic compaction is that, it is a little bit reminiscent of what you do in garbage collection. So imagine you are implementing a programming language and you are writing a garbage collector. Well, one way to implement a garbage collector is to say that you have a dedicated thread which deals with garbage collection. So once in a while, that thread kind of pauses all other threads and then runs garbage collection and then resumes your application. And that is kind of non-deterministic. But there is an approach to garbage collection which is much, much simpler. And that is you run garbage collection whenever you call malloc. So in the implementation of your malloc function, you actually have this condition which says, hey, if you're running low on free space, then you go and you do garbage collection just in time. Or you could actually, like, instead of only running garbage collection when you need to allocate something and there is no free space to fulfill the allocation request, what you actually do is that you could run a little bit of garbage collection every time you allocate. So again, kind of like you don't like, even if there is enough of free space, you still run garbage collection, but you don't, run your entire collection. You do just enough of it. And this is kind of like nice, simple system, which is deterministic and which naturally paces the speed of garbage collection relative to the speed of allocation, because you kind of like, you sort of amortize the cost of allocation, the cost of garbage collection over allocation, which is nice because, well, allocation is what creates garbage. So this is the approach we are going to use at Targetable. Whenever we accept a new request from the user and process this request and write some new data to disk, we'll also do a little bit of compaction so that we don't need this extra separate background process. And okay, the question is like how much compaction do we need to write? Okay, before we go to that, we have a question in the chat. Does deterministic compaction limit Targettable's maximum throughput compared to RocksDB, where compaction is allowed to run slower than commits to the log? Probably compaction is allowed to run faster than commits to the log in case of the RocksDB. So that is a good question. I'm actually not sure there is like, okay, so what we can't do in Targetable is that we can't really, like, dynamically make use of spare resources, at least easily. So we cannot do something like, hey, we notice that the cluster is idle at this moment, so maybe it's like night or something, so let's run more compaction like this. We can't do, well, maybe actually that's not true. Maybe we actually like can do this, it's just that it's like not implemented. But in terms of like actual throughput, actual concurrency that is employed by Targetable, I think that is like orthogonal. So we'll get to this issue. I'm not sure today because, like, well, it's kind of like okay. So let me say this. So okay, let's say that like you want to run compaction and you want to have high throughput. That means you need to utilize all of your available resources. You need to issue as much input-output requests as your disk can handle, and you need to issue as much CPU work as you have CPUs to process. And that kind of like means that you need to do stuff in parallel. That you kind of like, you need to try to compact many things at the same time. And if you are doing something in parallel, then kind of like it brings non-determinism back in. And this problem is actually solved. We kind of like touched a little bit on that when we were discussing preset. So what actually happens at Targetable is that, yeah, we kind of like are pretty flexible here. So there is no problem to say that, hey, we want our compaction to like occupy all your hard drive, all your CPU, and that's kind of like that works. Where we are less flexible is that like we can't really do like dynamic scheduling. So I think our architecture would allow us to do some kind of adaptive scheduling, but it like needs to be like coordinated cluster wide. So for example, like, as a part of the committing, each replica, for example, could record like its load average. And then the primary, when it collects load averages from replicas, it could decide that, hey, folks, for like the next so many rounds, we are going to increase our rate of compaction. So this kind of like possible, but it's not going to be like, super adaptive to conditions or in a specific replica. Yeah, this is like where like Tailbittle will fare worse than something like RocksDB. So suppose you have a cluster and replicas themselves have uneven load. So for example, each replica also has some noisy neighbors. In this situation, it would be beneficial to run compaction with different speeds on different replicas so that the replica compacts more when its machine is relatively less loaded, even though the rest of the cluster might actually be under high load at this point. We can't do this. For us, we have to coordinate the pace of compaction across the whole cluster. But given that the pace of that kind of like given this constraint, you actually, yes, you can be pretty flexible about how much compaction you actually run. Although we don't really do this, and I will actually explain this. So because kind of like like one mind state you can use here is to say, okay, so like compaction is work. Like compaction is like, I don't know, like cleaning your room. Like it has to be done. So kind of like let's like do it faster, so that like we have like clean room faster. Like let's kind of like try to proactively compact as much as possible so that we always have like the most compact disk, the most clean room. But Terminal actually is like it is extremely lazy. It uses like the opposite mindset, which is what is the minimum amount of compaction I need to be able to do to be able to proceed to the next step. And that is kind of like in some sense it's better because you are not like frantically at every point in time thinking about like, hey, I want kind of like the most compact disk possible. You kind of like you set up your target from the start, like, hey, I want like roughly this amount of like write amplification in my disk, and then you just like that like no matter what happens, your load for compaction is going to be pretty much the same. So okay, let's actually, okay, this is like super metaphorical, super abstract. Let's very concretely figure out like what do we need to do to, what is the minimal amount of work we actually need to do to get the compaction going. Okay, so where compaction starts? Compaction starts when we need to write a new table to disk. So remember, last time we discussed so-called mem tables, memory table mutable and memory table immutable. And the idea is that for compaction interval, which is 32 requests, cluster runs and just accumulates tables in memory. So this mem table is essentially just one big sorted array which of key values, which is a result of applying 32 requests, where each request, as usual, is itself batched. So in each request, we have around 8,000 transfers. So each compaction interval gets you, I have 500,000, but is it okay? 8,000 times 32, it is 250,000 transfers. Why I was thinking that we do 500,000. Well, I kind of like, that doesn't really matter. So basically, kind of like we accumulate 250,000 transfers, and then we want to push this to disk, and we want to push it to the topmost level because this is the fresh data, and this first data needs to like shadow everything that is below it. So what is the condition under which we could push data to the first level? And the constraint here is that each level in the LSM tree has only a finite number of trees. So there's like artificial bound which says, hey, level 0 can only have so many trees, and this bound grows exponentially. So it's actually okay. Let's slowly dive into the code. So we have this LSM grow factor, which means that the next level has LSM grow factor layers more. And kind of like, our like topmost layer, which is actually in memory, it's like one table. Then on the first level, we have LSM grow factor tables. On the second level, we have LSM grow factor square tables, etc., etc. So as you've seen, probably not because I was too fast, our LSM grow factor is 8. So each level has 8 times more tables than the previous one. So in terms of our picture, this one has 8, and this one has 64, and this one, okay, 64 times 8. I think it's like 5, 1, 12. Yeah, that seems like it, and etc., etc. So to push a table into a level, you need to make sure that this that the level is under limit. So if we want to move a memory table into our zeroth layer, we need to make sure that it has at most 7 tables, because if it has 8 tables, then it is full and we can no longer do everything about it. Okay, so suppose that actually we actually are at the limit, that our zeroth layer has 8 tables. What do we do here? Well, we compact. We take one table from this level and push it to the next level. So let's say kind of like picture looks, well, maybe something like this. So here I kind of like, so within each, so each rectangle is a table. A table is a sorted array of values. Within the level, all the tables are disjoint and they are sorted. So I use the width of a table to show the key range it covers. And in this picture, like this table intersects these 3 tables. It doesn't mean that this table is actually necessarily bigger because, okay, we kind of like glossed over this, but we'll probably need to revisit this. Each table actually is fixed in size. So for the memory table, we actually like know this limit because we know that memory table is the result of 32 prepares. And we know that each prepare can create at most 8,000 transfers. So we know that in the memory table, like the maximum size of our in-memory table is 250,000 of transfers. And that limit is actually going to percolate to all the actual tables on disk. So all those things, they contain, well, in case of transfers, like 250,000 top. But it might be the case that table has like 250,000 and it's like, very narrow, like all IDs are sequential, or it might be that, hey, there is a 250,000, but the table is like, somewhat elongated. It's like very sparse, so it covers large key range, but still it has like the same amount of values. So we could have like a picture like this, where like one table on previous level intersects in terms of like key range with many tables on the next level. But this is the key. When we merge tables, we never ever add values. We might coalesce two values if the key are the same. So the result might be smaller, but it is never going to get larger. So if we are in a position where our level 0 is full and we need to move a table to next level, we kind of like run compaction. And this compaction will create a set of different tables on the second level. But we know that the amount of values is not going to increase. And that means that compaction can create at most one more table on the second level. And that's curious. Like, we kind of like to be able to push mem table to level 0, we need at least one free slot in level 0. To get one free slot in level 0, what we can do is that we can push one table from level 0 to level 1. Well, level 1 itself might be full. And the condition under which we could actually push this table down is that, hey, level 1 has at least one single slot. And this is beautiful. So this means that we actually can immediately give a bound on the amount of compaction work we have to do worst case. Because worst case, for each level, we need to move only one table down if we maintain this invariant that, hey, each level has at least one free spot. So kind of like, yeah. Let's now kind of like think about this like a little bit abstractly. We have like our slightly uneven zero player. So we want to maintain this invariant that like every tail, every level has at least one spare slot. And if it is not the case, then we we'll start compacting. So we can push tables from one level to the next. And if you are a little bit proactive about this, you might notice that like, okay, so kind of like what is compaction? Compaction is like ultimately we read one table from one level, several tables from a different level, and we go and write new tables. So it is read, modify, write operation. But so it is like, we cannot simultaneously compact from here to here and from here to here. Because, for example, if we want to push this, down, but we also at the same time are pushing this down, then actually kind of like, by the time we push this table, it might no longer exist in this layer because it got compacted with the one with the previous one. So kind of like, yeah, you can't compact everything at the same time. But if you look at levels without a gap, with a gap, you can actually realize that, hey, those you could compact. Okay, Okay, I think. Yeah, those you could actually compact in parallel. So while you are moving this here, what you actually could do is that you could move this table here because it doesn't touches each layer which is written. So okay, this is kind of like starts sounding like a plan. We want to run a little bit of compaction on um, every commit of a state machine. And we actually want to run as little compaction as possible. And the amount of compaction we need to run is to just have one extra free slot in each layer. And we also know that hey, we actually can compact odd levels and even levels in parallel. And we know, like, the entire like time we have to run compaction is our compaction interval, our LSM batch multiple, which is this magic number 32. So kind of like, you are at the beginning of this 32 compaction bar, and you like look at this table and you realize, okay, so let's look at the even layers, and let's note all the even layers which are full. And let's go and push a table from each even layer which is full down to the odd layer, assuming that every odd layer has extra space, has at least space for one extra table. And once you do this, you kind of like realize, okay, so now all even layers have one free slot. In particular, there is enough of free space to push a memory table on level 0. But now your odd leveled layers are full. And that is a problem because on the next bar of 32 prepares, you are going to try to compact even layers again, and you need free space in the odd layers. So after we synced all the even layers, we'll go and do the same with the odd layers. So essentially, we split our 32 into halves of 16 and 16. So this is half and half. And here we compact even layers. And here we compact odd layers, which is pretty much how compaction works. You see, like very easy. And now we're going to start looking at the code and crying probably. Hopefully not, but well, we'll see. Okay, so let's start with. Okay, yeah, this is actually I believe we touched a little bit on this last time, but it's good to refresh this. So what kind of like, where's the entry point? What kicks the compaction? Compaction is kicked by the replica, where the replica says state machine, please compact. And compact here is a misnomer. This, why? Well, this is called after every commit. So we are looking at the commit dispatch loop. And this loop runs for every of those 32 prepares, which together form one large compaction. So the overall pipeline is that replica receives a request, replica replicates this request across backups. When it receives a quorum of acknowledgements, it knows that the prepare is logically committed, so then it executes its prepare, it commits it. After the commit itself, it runs this compaction call, and then it repeats this for the next prepare. So actually, this is not compact, but compact 1/32 fraction of. So kind of like we say, hey, kind of like don't like do the entire compaction. Do this like tiny fraction of compaction. And this op number is the thing which is like the conductor's stick. I'm not sure if it's actually called stick. Probably there is like, you know, probably it's a wand. It's like conductor's wand. This op number kind of like directs the compaction. It tells the compaction what it should be doing. So in particular, if this is like first half, if like op modulus 32 minus 16, then like even layers. And if this is the second half, then odd layers. Okay, so let's just see how it goes. Okay, so we have state machine compact. Just moves compaction. Well, important thing. This kind of like this is only a part of compaction, only 1/32th part of entire compaction, but it is still asynchronous. It still might need to read some data from disk, might need to write some blocks from disk. So that's why when we call compact, we pass this callback in, and the replica resumes commit operation only after compaction. So compaction blocks commit blocks compaction. They are like commit and compaction are pasted in the log step. Okay, so what do we do here? We go and call forest compact. Okay, and first thing we do, we orient ourselves about where we are in the context, in the compaction process. So the overall thing is called a bar, and one prepare is called a bit. So there are 32 bits in the bar, which is called LSM batch multiple, but really I should have renamed this to LSM compaction interval already. Okay, so we have first bit, then last half bit, then okay, and those are bit numbers. Then we have so this is something like U32. Then we have booleans, whether we are right at the middle of compaction and whether we are like at the last bit of compaction. Okay, and then we have this progress, which is how we looked at how forest open works. Well, anyway, but this is kind of like a nice pattern for asynchronous objects in TigerBeetle. Like, you know, like objects might do many different asynchronous operations. So forest can do open, then checkpoint, then compact. And this progress is sort of like a state variable, which simultaneously stores the callback and also tells you which specific operation is in progress. So we are compacting. So we say, hey, this is what we are doing. We are compacting, and this is the bit, well, in particular op we are compacting. Okay, so obviously at some point you need to start compaction process, and if you recall, if you imagine, like, you start with an empty database, like trivial checkpoint, empty log, and while you are committing something and appending something to memory table, for the current LSM batch multiple of prepares, you are compacting the previous compaction interval of prepares. But for the very start, for the first compaction interval of prepares, you don't do compactions. So this is what we are asserting here. Okay, so I guess I should start explaining compaction pipeline. Okay, yeah. So this is the terminology shift. So far, I was talking about, like, compaction as a single process, and, like, it is a single process. But in the source code, what we call a compaction, so like this compaction info kind of thing, is actually just this single arrow. So a compaction is a process where you take one table from some level and you try to push it down to the next level, merging it with all the intersecting tables from a level below. Okay. Compaction progress. Okay, so presumably compaction progress means like how, like where we are in the process of executing a single bit. And again, we start executing bit with this compact function, so this compaction progress should be idle. And I assume that when we call this actual callback, we'll assert that the compaction progress is idle. Okay, so then we say, okay, we start compacting, and okay, and again, kind of like as to hedge my bets, I kind of like, this is not a part of the code I'm like super familiar with, so you will be catching me like discovering unexpected complications. And this is actually the first unexpected complication, is that this compaction process manages both the LSM tree compaction as well as the manifest log compaction. How exactly? Well, we'll take a look at this. And as a reminder, we actually did study how manifest log compaction works, because it is much simpler than tree compaction. Okay, so then we call this bit function, which actually will schedule all the work. And okay, yeah. So this compaction pipeline is the thing which will handle compacting just the trees. And okay, so this is okay. I get it. Okay, I have fun for today. So I guess for today, we'll kind of like leave this, like, the actual meat of the compaction for later, and deal with like this smaller, simpler manifest log compaction. And for those who are joining late, compaction is the process where we optimize the storage of data on disk. So in particular, we have LSM3, and LSM3 has a property that it might store the same key on different layers, and only the first layer is what actually matters. And kind of like, in compaction process, we erase this data which is shadowed by the previous layer. And this is kind of like, this is an important terminology, and kind of like, if you like don't understand what is a compaction, if you don't understand what is an LSM tree, then, well, you have to like watch this a couple of times more, watch some of the previous episodes where we discussed an LSM tree, because yeah, this is like the core fundamental terminology. Okay, so kind of like assuming that we've somehow dealt with compaction of the tree, how do we compact the manifest? Which is, I think, something we should land to the code which we've seen. Have we seen this? Yes, I think we've seen this, but well, we'll see it again. So again, kind of like for manifest log, we compact it only twice during our compaction interval. So on the 16th bit and on, well, I think on the 15th bit, 16th, 15th, yeah, 15th bit, and on the 31st bit. So here, we compute how many input blocks we should read. Then we reserve the okay. Okay, well, let's take it slower. So what is the manifest log? That manifest log is what stores the information about our entire LSM tree, what tables are there, and how tables map to levels. And eternally, it is represented as a linked list of records, as a linked list of blocks, where each block contains a bunch of records which looks like append table address 64 to level 3. And kind of like, in a single, this record is like really tiny. So it's basically tables address, tables checksum level. So just like 64 bits, 128 bits, and like 4 bits. And this block is big. So the block is half a megabyte. So like inside this block, you have like a lot of those atomic records. So yeah, so let's say append here, and here we have a remove. So the semantics here is that at that point in time, this table appeared for the first time. Kind of like, because we are appending this to the level 3, that means that the why of why this table appears is that we were compacting from level 2 to level 3. So we took one table from level 2, a bunch of tables from level 3, then run this merge operation and wrote the results to the level 3. And this is like, this is how this table created. Then sometime later, we actually decided to move this very table with address 64 to the next level. So we run compaction. And then this table is no longer part of level 3. So we add this record to our manifest log, but hey, this table is now no longer needed. And now we can compact this manifest log itself, because these records kind of like annihilate each other. And again, we discussed this in details in one of the previous episodes. So right now I'm more interested in the overall flow of how this interacts with our compaction process. So okay, this compact and I want to say slightly more. So how compaction works? We for manifest log, we pick some tail of the blocks, and we compute the kind of compressed set of events, and we write the results to the beginning of our manifests together, importantly, with all the newly created tables. So this compaction of manifest log takes care both of compacting manifest log as well as externalizing all the tables which we have created, which is actually, I now understand why we are running manifest log compaction when we are running it. So you see, here we do this manifest log compaction on the half bar and at the end of the bar. And this makes sense because half bar and end of the bar is exactly where we stop compacting the tables. So by this time, these compactions have been run. So we created a bunch of new tables, and now we could actually go and externalize the newly created tables. So if we look at this manifest log, when we create a table, we call append on the manifest log. This goes to append internal, and then this table should go to some in-memory buffer. Okay, yeah. So this is like in-memory block which stores the new block of the manifest, and then this we write this new table into this block. Then we should be okay. We increment entry. Yeah, right. We increment the number of tables created, and if we have filled our in-memory block, we go and flip to the new in-memory block. So here we just finalize this block. We say, okay, now the pattern is zeroed. The checksum is set. Checksum, where do we? Okay, yeah, this is. We set the checksum, and we store. Okay, yeah, we store the finished block address in this log block address and log block checksums. Okay, and now when we do compaction, we should see the code where we actually write that to disk. So compact manifest log flash. Okay, right, yeah. So we have this count of closed blocks, and for each of the closed block, we just go and write this block to disk. And wait, but where is compaction? It is not compaction, it is just flash. But do we? Where do we actually do this? Okay, so yeah, I'm slightly confused here. I see the code where we okay. So I see the code where we are writing the new manifest log blocks, but I'm not seeing the code where we actually do compaction. So probably compact next block has to do something with this. So let's try to figure out where it is called. So okay, so compact with block and who compact next block. Oh, okay. Okay. Now it's it. So yeah, we like inside the compaction, we call flash to write all the newly created blocks, and as the callback to flash, we pass this compact next block, which starts the compaction process, where we read some blocks of the tail of the manifest log and kind of like compress it, look at which events from that block are still relevant, and ultimately I think we'll going to just append it to the beginning of the manifest log using the same append function, creating hopefully fewer blocks than we originally had. Okay, so this is kind of like makes sense, and I'm actually surprised that there is this nice cut point where I can avoid digging right into compaction pipeline. So compaction pipeline is for the next round, but you sort of like at this point you should have a rough idea of what is happening there, and that is that we should compact all the even layers for the first half bar. We should compact all the odd layers for the second half bar. And compaction means that we look at the layer, we check if it has spare capacity. We check if the level of the number of tables in the level is less than LSM growth factor, which is 8 to the power of this level. If this is already the case, then we do nothing. Otherwise, we should pick some table from this level and merge it with a table below. And I think that's going to be it for today. So thank you for watching. Thank you for joining this exciting episode where we start looking at the kind of the reason the rest of the code is written in Typeidle. This intricate process of compacting, and in the process of compaction, actually writing new data to disk. So thanks again for watching live on Twitch. If you didn't watch on Twitch but rather watched on YouTube, then thank you very much for watching nonetheless. And please join me next time at 5 p.m. UTC live on Twitch, or maybe a couple of hours after that as a recording on YouTube if you manage to miss the live show. And as usual, thank you very much for your questions and see you next week.